So today we'll talk about Dionysus as well as give a very brief introduction to another software called Perseus. So Perseus is a software for rapid computation of persistent homology. One can get the source code by clicking here. It will calculate a variety of different complexes and then calculate its persistent homology. Once you've clicked on source code, this will open up and you just have to see this here. Click here and that will download the software. And now that you've got the software, I just had it download into my downloads file, so I just was lazy and left it there. So I CD'd into the Perseus directory that I just downloaded, compiled it, which I can now do since I now have a C compiler via Mac ports and an online command thing. So I can now compile it. Now that it's compiled, I just need to create some data to enter into Perseus. And so I created a distance matrix. You can use any text editor you like, such as TextEdit. I probably wouldn't use Microsoft Word because it does more things besides just text, and I want plain text when you're entering in these things. You can always try creating it as a Word document, but sometimes letters don't actually get interpreted as actual letters by Microsoft Word. Many times they do, but not always. So TextEdit is a good one. That does give you a GUI interface similar to Microsoft Word. Or I like doing things within terminals, so I'll just Pico that. That will open up a screen. I can then enter some text, and then I can use Control-X to save. Sorry, Control-X to exit, and then choose Y to save, or I can do Control-X, Control-O. So Control-O will actually save. So here's the data file that I entered into Perseus. In this case, I'm putting in a distance matrix. If you read the instructions for Perseus, it describes the different formats. You can actually enter coordinates if you prefer. But in here, I looked at the example where we created a distance matrix. So I've got 3 data points. I will start off with my balls. So we'll start off with our balls of radius 0, so around each vertex. Around each vertex, I'll have a ball of radius 0. And then my step size will be 0.1, so I will increase my radius to 0.1 in the next step, to 0.2 in the next step, 0.3 in the third step, 4th step, and 5th step. And yet these are actually supposed to be all round balls, where the radius is either 0 to begin with, then 0.1, 0.2, 0.3, for a total of 5 steps. And then to save computation time, we set the maximum of our dimension to 2. You could set it to 3. You can set it to whatever you want to, but here in the example, it's set to 2. So, and then we can run Perseus. So when you run a C program, you can do the -- Perseus. And so this right here, the -- means that we will run this software right here. And then I've chosen the RIPS option. That means it's going to calculate a RIPS complex. And then the input here, this is my input, is this distance matrix. And again, you can have various different inputs. If I had wanted to, I could have then continued off this line and written an output if I wanted to go into a particular output file. Since I didn't specify the output file, it just went ahead and put it into output star.txt, and so it created 2 output files with the results. So you can look a little bit more at Perseus on the at the Rutgers tilde-vidit/Perseus site. It explains things pretty well, quick way to calculate persistent homology. But my main reason for doing this is just to mention that since we now do have a C compiler, you can install a variety of software packages. Now, this one, if you did not want to do the C compiler or you're on a PC and you haven't yet done it yet, since I'm only giving you Mac instructions, there are actually pre-compiled executables. You could have downloaded that instead. By compiling from source, you now have the source code and you can modify it. You can put it into other code. You can combine it with Dionysus if you want. So there's a lot of things you can do if you have the original C code. So it's nice to be able to do that. And the other reason I mentioned is just so I could get in a few more commands. I will frequently slip and call them Linux commands because they are Linux type commands, but I am doing all of this on my Mac computer. So that this should work, these commands should work on both a Mac and a PC. Sorry to those of you who have Windows, you can download some things so that you can also do this too, but those downloads are for the most part not trivial. If anyone has some good software for doing this on a PC, let me know, but the ones I'm aware of take a little time to install. Okay, so we will now go back to our Dionysus. So Dionysus. So it's Dionysus, and I also wanted to thank Dimitri, who is the creator of the program and also helped me install it. Michael also helped me install this as well, so thank you to these two for helping me actually get Dionysus installed and working on my computer. I had to modify a few of the commands on their website. So, and I will show you those commands. Any questions so far? So remember that Dionysus has two dependencies in addition to needing that C compiler that we downloaded last time. So we also downloaded CMake, and I also downloaded these header libraries from Boost. However, one has to install a few of them. So boost.python, most header libraries do not need any installation, but there are a few in Boost that Dionysus does use that do need to be installed. And so instead of downloading it, I'm going to delete a few slides and cut off some of the video from last time because instead of downloading Boost, it is a lot easier to use this command right here. So if you use this command, then you will both download and install Boost. All the dependencies will be made correctly, and so this is the quickest and easiest way to do that. If you know what you're doing, you can install the needed components for Boost, the Boost Python, by looking at the Boost support pages, but this does it all in one fell swoop, and I like things that are quick and easy, so this is what I did. But I should note that I did get a warning when I typed this command on my Mac, and that's because when you do the sudo command, you just made yourself a super user in order to install software. And so that's why you get this warning, is because we are now installing software. That means that if you already have some software that interacts with Boost, Boost might overwrite some things that you might not want overwritten. Now for me, it was perfectly safe to run this command because I've always done my programming on a Linux box. This is the first time I've looked at programming on my Mac, and I've never used Python, so I didn't worry about this writing over things that I'm currently using. So for me, there was no harm at all in writing this. If you are using Python, I don't know if it interacts with any of the Python things. Is anyone familiar with Boost and aware of that? But if you are doing any programming on your Mac, especially with Python, you might want to look in to see if there are any conflicts between this method of installing Boost and what you're currently running. But if you're not currently doing any Python or other programming, then doing this command is perfectly safe despite the warning. So, but you do have to enter in your password, which, I did into my computer, so it did install. So that was a nice quick install for Boost. Any questions there? The other thing that one needs to do is add a path. So you need to add a path. Again, you can use any text editor you like as long as it is a plain text editor. So remember, text edit from that Persicius slide. So text edit would be one thing with the GUI interface. I'm old, though. I don't like GUI interfaces. I'm used to Pico, similar to Nano. You can use Emacs, so Emacs is another one. So I Picoed my .bashrc file. But before I did that, I created a backup. So especially if you're new at modifying your .bashrc file, you don't have to actually enter a password, but this is more dangerous than what I did before, because this sort of helps run various things, and if you mess this up, it can cause you problems. Now, if you do mess it up, it's easy to go ahead and put it back to what it looked like. But you might not know what it looked like unless you create up a backup file, and so I copied my bashrc file into .bashrc backup. So now I have two copies, so if I do something odd and I can't figure out what it is I changed, well, then I can go back and look up my backup. I did forget one command here, is that if I was in some other directory, to get to my home directory that contains my bash file, I can just type a cd. CD, change directory without any specification, will put you into your home directory. And so I am now in my home directory. And so now I can work with my .bashrc file. So any questions there? So using any text editor, so I opened up, so I Picoed in my home directory. So in this home directory, I typed the command Pico, not Pica, Pico, .bashrc. That opened up a file at the very end. Doesn't have to go at the very end, but that's where I put it. I put this command right here, and that will set my Python path to look in Dionysus to find this thing right here. So note that I did put Dionysus in my i.cycle, because remember last time when I ran this command to download Dionysus, I ran this command to download Dionysus, and I ran it from my home directory. Since I ran it from my home directory, it's in my home directory, and so this file is actually in my home directory, and this tells me to put it in my home directory. If I had instead been in my downloads directory, so if I had been in my downloads directory when I ran this thing to install my Dionysus, well, then I would have wanted to go to i.cycle downloads, and so that way I would be pointing my Python path to the correct location of wherever I downloaded this thing into. So any questions up through here? So add this path, just modify the path to wherever you happen to put this thing right here, and wherever you put it, that would be this directory right there. And then you put in your Dionysus. Dionysus this does not yet exist because we have not yet created it, but we will create build/pythons /python. So we will be creating this, so this will exist very soon. questions up through. So this path is not yet active. So just like sometimes when you do software updates, you have to restart your operating system to get those updates effective. It's the same thing with path. I kind of need to restart my bash. I can do that by opening up a new terminal window or from my home directory. So if I get into my home directory with the cd command, I can type this, and this will actually sort of restart my bash. That might not be the correct terminology, but it does get my path set to whatever I had newly modified. And I can check to see if my path is set correctly with this one right here. And so you want your path to say wherever you put your Dionysus. I put it in my home directory, and then we want these things that we will create very soon. Any questions up to there? Check to make sure your path is set correctly, and if it's not, you might want to either open a new terminal window or make sure you saved the path when you went ahead and entered it in. Okay. So now we're ready to start compiling Dionysus. So following again the instructions on the Dionysus website, we cd into the directory, we make that directory build, we cd into build, we do CMake, which will create the make files, and then we'll do make to compile those make files, to compile Dionysus. However, this is where I ran into problems. Even though my Mac is a little bit over a year old, and this late summer I updated to the latest Mac operating system, Mountain Lion, and I haven't done any Python programming at all. Well, it found the wrong Python. So CMake did not use the right Python, so it wasn't because of the path setting up, because that did not yet exist. So it looks for other things first. But it didn't find it, so I had to run this CMake command here, all of this instead, so that it would find the right Python. So you can try this to see if it works for you. And if it doesn't, you might need to modify the CMake command, and that's what I had to do. Let's take a closer look at the CMake command. Since there was no way for Dimitri to know my system, he sent me a command, but it didn't have the completely accurate direction because he doesn't know my system, because it's my system. So I had to find a few things. So let's go ahead. You might have to change this command too a little bit. So let's see if we can understand the various steps. The CMake, that's that software that we downloaded last time, and that will create the make file using CMake. This ... means that I'm going to go up one directory. So that was actually the same thing that was up on here. Is the first thing we do is we do a CMake, but we go up one directory. So we're creating make files using things down here, but everything we get created are going to be created in build. So before you do CMake, if you do an ls command, you will see that there is nothing in build whatsoever. But if you do after your ls command, after your CMake, you will see that a number of things have been created. And so in the build directory. So we will run CMake to create files in the build directory and potentially elsewhere, going up one directory. And now I am telling them which Python to use. So this first -d Python _ library equal to tells which Python I want to use. And I want to use Python 2.7, which is in this directory right here. How did I find that directory? Well, I just CD'd into my library and looked to see where I had Python. So what was the name of the Python? So I CD'd into here. This backslash will take me, no matter what subdirectory I'm in, it will take me to my /opt directory. And then I can do this ls command to list all my files, but there are an awful lot of files in the library. And so I use wildcards before and after, and that way any file that has Python in the middle, it will list, ls will list this where Python is in the middle. So I use these stars, so it will list only files that contain Python. And by middle, maybe the wildcard, there might be nothing in the beginning, that's fine as well. So it doesn't have to be, there doesn't have to be characters before, there doesn't have to be characters. So this would also find, you know, Python dot something other if that was also in my library. But now I notice that this is what I needed, this one right here. And so I went ahead and did this thing right here. So I didn't want to just use Python. I want to use Python 2.7 until I did this command right here. I didn't know I wanted Python 2.7, but that's what I had, and so now I know I need Python 2.7. So that gave me this right here. Well, then I need Python header files. Didn't really know where those are, so I, followed a sample which did not have the header files in the location of the sample, but I got an error that it couldn't find this particular header file. So I ran a CMake command that was similar to this, but this last part here was actually not correct. But I used the error that I got saying that it couldn't find. What it couldn't find was this file right here. It couldn't find that file. So that meant that I could grab this thing here. So I looked for pyconfig in my contents of Python 2.7, and I piped it into grep. Grep is a great command. You might want to man it if you want to read more about what grep can do. But I grabbed it basically, and so now I know that this right here, so up to the backslash, will include all the header files, not just pyconfig.h, but all the header files that I might need. And so that is how I got this second one right here, how I knew where to look, what library, where my library of header files was. So that's my CMake command. That was a CMake command that worked for me. You may need to modify the CMake command to make it work for you. Any questions here? Okay. So we are now ready to actually compile. So we compile nice and easy with a make command. So things are much easier from here on out. There is several example files within Dionysus. One of them is the triangle example. Within the build directory, there is something called triangle. So if I cd from the build directory into example such triangle, there is an executable that you can run. However, I wanted to take a look at the code, so we are going to look at the triangle example, the Python code within Dionysus. So we'll look at the actual code. But that means I needed to get into the right directory, so I did a print working directory to see where I was. I wanted to go back up to Dionysus, so I was in triangle, so I cd'd ... to move up 1 to examples, did another ... to move up 1 to build, did another ... to move up to Dionysus. There's other ways of doing those CDs as you've seen before, but this now got me into my Dionysus. And now I'll go into example/triangles. So notice that within Dionysus, there's many subdirectories. We were in build, which did contain examples, which did contain triangle. But within Dionysus, there is also another directory called examples, which is different than the build subdirectory examples. There's also an example subdirectory within Dionysus that's different, and a triangle. And so these two triangle directories, this triangle directory is different than this directory. This is a subdirectory of examples, which is a subdirectory of build, but this is a subdirectory of examples, which is a subdirectory of Dionysus directly. So I got into my triangle directory, but the one that is on this branch of Dionysus instead of the other one. Questions there? So now that I am in the directory, if I did an ls command, I would see that there is a triangle.py, and so I can run the Python code with, remember I had to use Python 2.7, so my Python, if I just do Python, I actually get it to crash. So I have to use Python 2.7. That's my working Python. So I do Python 2.7 triangle.py. You might just have Python, in which case you might not need the 2.7. So depending upon which version of Python, if you didn't have to do that long CMake command that I did, then just Python triangle.py should work just fine. But for me, I needed the Python 2.7. Questions up through there? Okay. So there is another way of running Python, and I can actually run it anywhere. So just to show that, I CD'd into my home directory, but I didn't need to. I didn't need to do this at all. I could have run Python in any directory. So I run Python 2.7. It opens up Pythons, and it gives me command line windows. So now I can type various commands straight into my Python. Just like when we were running MATLAB, we typed it straight into MATLAB. I then tried to create a simplex, but I, of course, got an error because Python itself does not have Dionysus. So just like with MATLAB, if you want to load certain things into MATLAB, you have to type it in. If I want to load something into Python, I'm going to have to import things into Python. And so I need this command. But once I have this command, I've now actually imported everything into Python. You don't need to import everything. So if you take a look at, we'll actually take a look at the triangle.py, in which case only a few things from Dionysus were imported because not everything was needed. But if you're not sure what your needs the star, that wildcard, we can just import everything. And now when I do s equals a simplex, I actually do create the simplex 012. We can run Python, via command line, but I want to go back to this triangle.py. It's usually easier to write a Python, program, and that way, if you want to modify it, you can just, modify it within this file. You have everything in nice, neat, and easy to read. And so this is the file triangle.py. So right here, I've got my triangle.py. So you can see in this case, what are we importing? We're importing simplex, filtration, static persistence, and these other things. So this is what has been imported from Dionysus. That's the only thing that you need. If you prefer, because if this is too long to type, you can always import everything and just put in the wildcard. And then in triangle.py, a simplex is created. A simplicial complex actually is created. And many, many simplices, creating an entire simplicial complex is created. And we can see how to create a simplex. We are going to create the vertex 0, 1, 2, the edge 0, 1, the edge 1, 2, the edge 0, 2, and the face 0, 1, 2. That is why this thing is called a triangle, because we created 3 vertices, 3 edges, and 1 face, i.e. we created a triangle. And then there are these real numbers. These real numbers are basically our times. They don't have to be our times, but they can be used basically to order when these simplices enter into our filtration. So we can use these to create these real numbers here to create our filtration, and they can be any real numbers. I think we want to start out at 0, though. There was one warning, and I can't remember what it applied to not use -1, and I can't remember if it was for vertices or time. Sorry, I'll have to go back and read the directions for that. But that is explained on the Dionysus website. Any questions on how to create a simplicial complex? There are also other examples on the Dionysus website on how to create a RIPS complex from data points, how to create the 8-dimensional sphere. So there's lots of ways of creating a complex. But we're going to stick to this very simple example and take a look at that one first. We now have a complex. The next thing, so on here, all the blue is code that's actually in the triangle.py. So this is, I now have broken up. So I was showing you part of the file, triangle.py, and now I'm showing you more of it, but only a piece at a time. So if you Pico or text edit, you will see all the blue. You won't see the black or the green. Where the black comes from, that comes from me actually the output of running triangle.py. So if I type Python 2.7 triangle.py, or if you type this, or Python triangle.py, that will run triangle.py, and we start seeing the output. And I basically just divided the output to say what was giving me the output. This first thing here, I can see what this does right here, or this thing right here. What does this do? It prints complex colon. So if you do with the quotes around it, then you just get the output, whatever is in here gets printed. But then we have the command complex, and that will actually print our complex, which we entered in, remember, 3 vertices, 3 edges, and 1 face. So that's our complex. We can also print the word vertex. So I'm printing the word vertex right here. And now I'm doing this sort. So remember, when we do persistent homology, we want a filtration, we want a sorting of our simplices, and we would like our simplices to enter in one at a time. And so this is one way of sorting your simplices so that they enter in one at a time. And we are sorting our complex. So that was the complex that we created right here. So this is the complex that we're sorting, this triangle. So we are sorting that complex. And how we're sorting it is using vertex underscore comp. So this is how we're sorting for this particular example. In this case, we're actually ignoring the real numbers. We're ignoring all these real numbers right here. They don't even need to exist when we use this one here, because it's comparing 2 simplices with respect to lexicographical ordering, the dictionary ordering. So if I were to open, read these simplices in a dictionary, well, 0 comes before 1, so everything where the first entry is 0, that's going to be first on my list. Then in order to compare the next thing, well, one comes, the shorter words come before the longer words, and one comes before two. And so this is our ordering in terms of the lexicographical. You just compare the first terms. If this is larger than this, then this comes later. If they are the same, then we take a look at the second terms. And if the second term, the empty thing comes before the non-empty, one comes before, and if they're again the same, then we can compare, or one comes before two if they're two different things. So we do have the choice in terms of our filtration of just choosing the lexicographical ordering. So, and that was just specifically with this command right here. We didn't have to print this vertex here, but it was nice to see that this was just with our lexicographical ordering. We probably don't want lexicographical ordering, so let's look at a couple of other ways of ordering it. Two other ways of ordering it is with respect to our actual real valued, the real values. So if I go back up here, what I would like to do most of the time, I want to use these values, these real values right here. I would like to use those to order my simplices. If I want those real values to order my simplices, so I want to think about those as time, then when I sort, I want to use data underscore comp. So data underscore comp is explained in green right here. It compares to simplices using those real values. So that's usually the one that you're going to want to use. I forgot to say what my coloring meant on my slide. I said already that the blue was from our triangle.py file. This is the output when I run Python 2.7 triangle.py. The green is explanation that I took from the Dionysus website. So if you go to the Dionysus website, it will explain all the different things that you can do within Dionysus. It explains the code, and so this tells you that it compares the two simplices with respect to the real values. Any questions up to here? So there is one other ordering that also might be useful, and that is this ordering right here. What it does is it says it compares the two simplices with respect to their dimension first, and then uses the real numbers. So if you want to put in all the vertices first, and then all the edges, and then all the faces, regardless of what real numbers have been associated with them, then you're going to want to use this command here. And that way it'll do vertices first, then edges, and then faces, regardless of the real numbers associated. If I go back and look at my complex, well, the vertices numbers are lower than the edges, which is lower than the face. So in this case, the two commands would do exactly the same thing. But if I had, for example, put in a 5 here, or a 6, so 6, 5 already existed. If I put a 6 in right here, that first command would have put my 0 simplex last. It would have put my vertex 0 last, which would be a problem because I need my edge, my vertex to exist before my edge. If, however, I could have, however, put this thing, so I could have changed this thing to a 3, in which case I would have created the vertex 0 first, then the vertex 1, then the edge 0, 1, and then the simplex 2, using that data underscore comp. If I did the one that respected the dimension, then it would have still done 0, 1, and 2. It would have done all the vertices first, and then it would have done the edges, even if the 3 is greater than 2.5. So that's the difference between these two, is this one will just take those real numbers and give you that ordering. This one will actually force the dimension to take precedence, So it will do vertices first, then edges, and then continuing on with higher dimensional stuff. Questions there? Now we're ready to go ahead and get our filtration. We are choosing our real numbers as our order. And so we now have our complex in the actual filtration order. And this would be in our increasing real numbers. Then I can go ahead and calculate my persistence and then decide to just print persistence initialize. So persistence initialize is printed. And now we can go ahead and do the pair simplices. So remember the algorithm that pairs the simplices so that if I first create a cycle, in this case my cycle is the vertex 0, create another cycle, my vertex 1, create another cycle, my vertex 2. Oh, when I create, so those are all positive simplices because they create cycles, they create actual generators in my homology. Oh, but when I add an edge, I've now destroyed, I now have a negative simplex, so my edge is a negative simplex because now I've destroyed this cycle here. 1 is now related to 0, it's now in the same equivalence class, and so now I only have 2 components instead of 3 once I add this edge. And so we now pair, we will pair 1, that positive simplex, with the negative simplex 1, 2, for which we use to destroy it, for which we modded out by it to say that we do not need separate classes for 0 and 1. Oops, that was supposed to be 0, 1. Yeah, so this is the edge 0, 1. So 1 is paired with the edge 0, 1 because it destroys 1. It puts 1 into the same equivalence class as 0 in terms of the homology. So, so this will pair the simplices, and in green you can read in the Dionysus website what that does is that it will pair the simplices using that positive negative simplex algorithm. Store underscore negative just says whether or not you want to store the negative simplices. Maybe you don't want to store the negative simplices. Maybe you just want to know the generators. But here we're actually going to store the negative simplices as well, so we will also know what our negative simplices are. So since we set it equal to true, the default is false, but we put it equal to true, so we will be storing. So we will store the negative simplices as well. Then we've got this thing right here where we will go ahead and look at what our pairs are. We're going to look at these commands first. For all our simplices, so for all our simplices, we're going to print the sign of the simplex plus the pair of that simplex. So the sign of the simplex will be true if it's a positive simplex and negative false if it's a negative simplex. So in this particular case, 0 never got paired with anything. So this was a little bit of a weird case. 0, we had 1 gets paired with 0, 2 gets paired with 1, and then we have a positive simplex. So this never got paired with anything, so its pair is just 0. And so we print the vertex 0, we print its pair, which is 0, and we print the sign of it. 1 is the same thing as plus is the same thing as true. So 1 means it's a positive simplex. We'll ignore the cycle until we have a more interesting example. So let's take a look first at the vertices, though. So with the vertices, we have that this was at step 1. We entered in vertex 0, and it did not get paired with anything. At step 2, we have vertex 1. We know that eventually at some later step, it will get paired with edge 0, 1, so that's its pair. So this is its pair. We printed 1, and we printed its pair, and we printed this one right here, meaning that it's positive. We print 0, meaning that it is negative. So this is negative. We also print true for positive, minus for negative. So if this thing is true, you'll have a 1 here. If this thing is false, you'll have a 0 here. So if your simplex is positive, it'll be true and 1. If your simplex is negative, it will be false and 0. Let's take a look at the rest of that code. So we have, now we're going to add in our edges. So in our first things, we will again be printing our Simplices, and I should have included that code here. So we printed the sign. In this case, it is true or false, the sign and the sign of the pair. So we print also here and here the sign and the sign of the pair, but in this case it's 1 and 0 for positive versus negative. Here it's true and false versus positive or negative. We also printed the simplex. So this right here is the simplex and its pair. So the simplex and its pair. And so that's what we're doing in these first things, is printing those two. Let's take a look at the third one. The third one prints the cycle. So in this particular case, I actually have that it's not so much that we're printing a cycle, it's that we're actually printing a boundary. So what we had is that we are killing a cycle. So the reason it's called cycle is because 1 was a cycle. It was a cycle if 0 entered in at time 1 and 1 entered in at time 2. It was a cycle at time 2. And then 2 entered in at time 3. And then at time 4, it got killed off. So 2 units later, its persistence was 2. So this right here is the persistence. And that's this thing right here. We're doing the length of this cycle. And so we are putting in, we're printing cycle. The %d corresponds to this first quantity right here. We're doing the length of the cycle. The cycle is the whatever 0, 1 is paired with. 0, 1 is paired with 1. So we know that the length of the cycle 1 is 2 right here. And we also know that it got clobbered by the edge 0, 1 joining to 0. So if you remember that algorithm, that's what this thing is doing with respect to. We won't go into this. This is actually not the boundary. For this example, it is the boundary. But remember, it was not the boundary. Sometimes in order to go to pairs, we might have already chosen part of the boundary, so we wanted to go backwards a bit more. So if you remember that paper, sometimes we had to go back a few more before we actually found the pair. And so this is the sort of thing that we then also associate with it as well. But in this case, our sample is too simple, so we're only going to see the boundary, but you can get more complicated things as described in that paper. So then we continue on, add in the edge 1, 2 at step 5, and so that killed 2 units later, so that is That's persistence. We then add in the edge 0, 2 at time 6. So at time 6, we add in the edge 0, 2. That actually creates a cycle, and so that's why this thing is blank, since it's a positive cycle. Since 0, 2 is a positive cycle, we don't have any cycle. So it's only when we've got a false here that we will then have something interesting when we're killing off something that we will say what our persistent is. The last thing is we then add the face, and so our face got paired with the edge 0, 2, and so that got killed off, and so that implemented that method. I had hoped that we would have time to go over the zigzag complex, but we will very quickly go over the zigzag complex on Wednesday, and then also start cohomology. But the zigzag complex won't take very long to discuss. But there are many ways of calculating persistent homology. So there are many ways of calculating persistent homology within Dionysus, and it can do cohomology as well, which we will start discussing on Monday. Any questions? Well then, see you next time.